This is the first video on intermolecular forces that we like to call IMFs, the three little letters that you may learn to hate or love. So let's talk about the first IMF, and that is London dispersion forces. So intermolecular forces are the forces between molecules, not intra. That would be the force inside of a molecule or the chemical bond. So I have two hydrogen chloride, hydrochloric acid molecules side by side. And so you can see that the bond energy that's holding the hydrogen and chlorine together is really, really strong, 432. But then the intermolecular force, the force between those two molecules, is only 30. So we're talking about the attractive forces between molecules. That's what we mean by IMFs. Now, what those forces are has a whole lot to do with what types of atoms are bonded together. And you're going to learn how to predict what IMFs are present for any molecule or substance. So let's talk about the first one. The first one is London dispersion forces. We often call that dispersion. You may see LDF. Now these are very weak forces generally, and this one sounds a little bit weird, so stay with me on this example. Let me show you a molecule, okay? And it's got electrons, right? Could the electrons randomly end up maybe more toward one side of the atom? They are moving, right? Could they? Maybe. Well, temporarily that would cause a very weak dipole. And then what if there was another molecule right beside it? What would that temporarily separation of charge do to that molecule next door? Well, it would kind of separate the charges in that molecule. So this weak temporary separation of charge causes a little bit of, guess what? Attractive force temporarily between these two molecules. This is dispersion force. So all atoms and all molecules will have London dispersion forces. So what kinds of things could cause those dispersion forces to be significant? Well, a couple things. One would be the larger the atom, the more electrons, the more polarizable, the more electrons that could separate and end up causing a separation of charge. And then the shape. If it's a long skinny molecule, maybe a big long hydrocarbon, those molecules have greater dispersion forces than little short fat ones. So let's do a couple examples. Helium versus xenon. Well, they're both noble gases, but xenon is much, much larger, and it's got many more electrons, and so that one would have greater dispersion forces. Bromine and chlorine, again, they're both halogens, but which one has, they're about the same shape, but bromine has many more electrons, and so it would have stronger dispersion forces. And then I've got two hydrocarbons there, and the one that is longer and has more electrons will have greater dispersion forces.